So here is another nice polynomial problem. Problem states a monic polynomial p with the real coefficients satisfies that mod of p of I is smaller than 1. Prove that there is a root z is equal to a plus ib of p such that a square plus b square plus 1 whole square is smaller than 4b square plus 1. For solving this problem, we have to first look into the form of polynomial in terms of its root. So we can simply say that if p of x is any polynomial, then we can write it in form of its root, which is x minus alpha 1, x minus alpha 2, up to x minus alpha m, where alpha 1, alpha 2 and alpha m, all these are the roots of a polynomial. And if you are talking about a polynomial on real number, so it may have a complex root, but if z, which is in form of a plus ib, is the root of polynomial p of x, then it simply implies that z bar, this is the conjugate. It has a definition a minus ib with the negative sign, must be the root of p. So this is the very important rule for a real polynomial. Means if polynomial having a real coefficients, then any complex number, if is a root of that polynomial, then its conjugate must have to be the root of the same polynomial. So we are going to use this idea. So first we write the form of a p. Let's say there is some roots are real and some roots are complex. So we can rewrite it like x minus alpha 1, x minus alpha 2, up to x minus alpha m. And except these m roots, there is few more complex roots, which are x minus z1, and since its conjugate must have to be the root, so we can write it like x minus z1 bar, and this will continue up to x minus z sub k multiplied by x minus z k bar. And now nothing we have to do, just apply the condition that is given. We know that mod of p of I is smaller than 1. So we can put the value I in place of x and make this inequality. So I minus alpha 1, I minus alpha 2 till I minus alpha m. And now we have to apply the same in complex part. So I minus z1 multiplied by I minus z1 bar, and it will continue up to I minus z sub k multiplied by I minus zk bar. And now we are taking the mod of this whole term, and this expression is less than 1. We know the one property in modulus, that mod of AB is equal to mod of A multiplied by mod of B. So we can decompose this modulus. So we can rewrite it like mod of I minus alpha 1 multiplied by I minus alpha 2. Same for I minus alpha m. And now here comes the tricky part, that I'm going to pair them, and we'll put this pair inside the mod. So we can write this I minus z1 multiplied by I minus z1 bar. Similarly, we can take this pair inside a mod, and we can write it like I minus zk multiplied by I minus zk bar, which is lesser than 1. And now we know that there is some root in a complex number. So let's say, without loss of generality, z1 is that root which has a form a plus ib. So what we can say, that inside a mod I minus a plus ib multiplied by I minus, since this is the z1, then its conjugate c1 bar would be a minus ib. We can replace it by this a minus ib. And now if we multiply this, we'll obtain minus 1 minus of a plus ib multiplied by I minus of a minus ib multiplied by I, and the last term would be a square plus b square inside a mod. And we're taking it smaller than 1. Here is the one reason that if you think carefully, then each term in the real part, we can write them like I minus alpha 1. We can write this the square root of 1 square plus alpha 1 square. So alpha 1 square is a positive number, and we know that it never can be lesser than 1. So these all terms can never be less than 1. So for holding this condition, the inequality is less than 1, we have to take at least any one number in this complex part which is less than 1. So I assume that term is this form. So I assumed that this term, which has a form of a plus ib as we are given in our problem, is less than 1. And now I'm going to rewrite this expression, and we can write it like minus 1 plus a square plus b square, and we can take I common, and we can say that minus of I multiplied by a plus ib plus a minus ib smaller than 1. We can simply cancel out these imaginary terms, and we'll get a square plus b square minus 1 minus I of 2a smaller than 1. And if we take the modulus of this, then we can say that a square root of a square plus b square minus 1 whole square plus 2a whole square is less than 1. And if you solve this inequality, then you can simply obtain the result that a square plus b square minus 1 whole square is less than 1 minus 4a square. But if you look back to your statement that you have to prove, so here is the inequality where in the right side 4b square plus 1 is as a term, and here is a plus. So we can say that we not got that result, but this is the equivalent of saying that, and we can simply prove it after doing some more maths. So first let's add the 4b squared term in the right side because it's not there for now. So what we can do that by adding up the 4b square in this side, and since we added a new term, so we have to add this in both sides, so 4b square over here also. Oops, this is minus, and now we have to again do some maths for solving this large expression. Square, we can transfer this 4a square in the left hand side, and we can say that 4b square plus 4a square is smaller than 1 plus 4b square. And then we can rewrite this minus 1 like plus 1 minus 2, which is same as saying minus 1. One plus 4b square. And if you use the formula of a minus b whole square by assuming this whole term as a and this 2 as b, so you can rewrite this a square plus b square plus square plus 4 minus 4 a square plus b square minus 1, and the rest of the part is same, square, which is less than 1 plus 4b square. And you can simply see that this whole term is going to be 0, and you are left with a square b square 1 whole square is smaller than 1 plus 4b square. So that was a simple mathematical work, and we can see that these two inequalities are equivalent.